The Earth is a cosmic laboratory, shaped and reshaped by countless chemical reactions. Certain fundamental factors influence these reactions and the rates at which they take place. Exposure to air and water slowly causes iron to rust. When iron rusts, it reacts chemically with oxygen. It's a slow, almost imperceptible reaction. We can produce the same reaction in a laboratory. Instead of an old wagon, we'll use steel wool, which is mostly iron. Instead of air, which is only 20% oxygen, we'll use pure oxygen. Here's how iron can react with oxygen, quite a bit more violently than it normally does in nature. Some of the wood in a match burns, reacting with oxygen in the air, and in a few seconds, the charred part is mostly carbon. But for a prehistoric forest, buried by vast cataclysmic changes in the earth, it will take 1 million years for its wood to undergo similar chemical reactions that also turn the wood to carbon in the form of coal. Reactions take place at different rates. Into 2 beakers, we pour dilute hydrochloric acid. A sample of magnesium on the left and iron on the right will be dropped into the acid. The metal magnesium reacts rapidly and violently. But in the other beaker, the metal iron rests on the bottom, reacting slowly. Once again illustrating a basic idea. Different reactions take place at different rates. But why? The answer relates to chemical bonds. In reactions, chemical bonds are involved. Some breaking, others forming. The factors that control the rates at which these changes take place are the factors that control rate of reaction. At room temperature, there's almost no reaction between methane gas and oxygen. The heat of a flame is required to start the reaction. But at the same temperature, nitric oxide, NO, one of the products in automobile exhaust gases, oxidizes moderately fast into brownish nitrogen dioxide, NO2. This is a reaction involved in the production of smog. Here are the 2 reactions. One, extremely slow. One, moderately fast. The difference in reaction rates lies in the difference in the nature of the reactants, methane and nitric oxide, which leads us to our first point. The rate of reaction is affected by the nature of the reactants. In the moderately fast reaction between nitric oxide and oxygen, only a few relatively weak bonds have to break. In the extremely slow room temperature reaction between methane and oxygen, many strong bonds have to break. Generally, the stronger the bonds, the slower a reaction rate will be. And the strength and number of those bonds depend on the nature of the reactants, one of the several factors that influence reaction rates. You don't usually think of wheat as an explosive, but when wheat or other grain is loaded into grain elevators for storage, dust from the grain fills the air inside the elevator. Just a tiny spark or flame, and this mixture of wheat dust and oxygen in the air can react extremely rapidly and explode violently. And yet, when the elevator is packed solid with grain, there's very little danger of explosion. Many solid substances that react slowly in large pieces react rapidly in the form of dust. Coal burns slowly, but coal dust burns explosively, which leads us to a second factor affecting reaction rates: the surface area of solids. Coal is essentially carbon. When it burns, atoms of oxygen react with exposed atoms of carbon. Only those on the surface exposed to oxygen can react. If we cut the piece of coal in half, more area is exposed to the oxygen, so more reactions can take place at the same time. The rate of reaction is going up. Each time more surface area is exposed, the reaction rate increases, as long as enough oxygen is available. Eventually, if the lump of coal is converted to tiny dust particles, the surface area available for reaction with oxygen is increased tremendously, and the reaction rate is so rapid that an explosion results. Surface area is significant when solids, or substances in different phases, are involved in a chemical reaction. To illustrate another factor, we can let a dilute potassium iodate solution react with an acidified sodium sulfite solution that contains a starch indicator. The solution will turn blue when the reaction, which involves several steps, nears completion. The solution turns blue in about 35 seconds. Now, using a solution of potassium iodate that's 10 times as concentrated, we allow them to react again. Now the solution turns blue in only 20 seconds rather than 35. Illustrating this point, rate of reaction is also affected by the concentration of the reactants. Electrolytically, we can break apart the compound water into its constituent elements, hydrogen and oxygen. Once hydrogen gas forms, we can easily recombine it with oxygen in the air. It seems like a rapid reaction, but compare that with this. In some liquid-fueled rockets, liquid hydrogen, much more highly concentrated than the gas, reacts with liquid oxygen. The reaction proceeds at a very rapid rate, almost a controlled explosion. Concentration clearly makes a difference in the rate of reaction, and so does the temperature of the reactants. In the frigid ice fields of the polar regions, there's little decay. Food left behind by polar scientists has remained fresh and edible for 50 years or more. But in the tropics, the chemical reactions of decay proceed at a rapid rate. In tropical heat, foods spoil quickly and easily. Every time a fuel is ignited, it's a demonstration that reactions that may take place extremely slowly at room temperature can be sped up considerably when the reactants are heated. The fact that concentration and temperature of reactants both affect reaction rate can be explained by the same concept: collision theory. According to this theory, reactions occur when colliding particles momentarily form an activated complex. Then the complex falls apart into new compounds. In any particular reaction, the more particles that are crowded into a given space, the more collisions will take place. This is what happens when we increase the concentration of reactants. A greater concentration leads to more collisions, and more collisions in a given unit of time make a faster rate of reaction. Collision theory also helps us understand how temperature affects reaction rate. When a reaction gets hotter, on the average, its particles move faster, collide more frequently, and with more energy. Now, many collisions are duds. They don't have enough energy to form activated complexes. Or if they do, the complexes fall back into their original configurations. Collision theory suggests that an increase in temperature reduces the number of duds in a reaction. Here's how. Let's think of a reaction in terms of a hill and a ball. In order for the ball to roll over the hill, it must have a certain amount of energy. We can think of this as the activation energy for a reaction. If colliding particles have enough energy, activation energy is achieved and a reaction takes place. For every reaction, there's a particular minimum activation energy needed before a collision can be successful. If particles collide too gently, or with an orientation that requires more than the minimum energy for the reaction to occur, activation energy might not be achieved, and no reaction take place. An increase in temperature increases the energy of the collisions. A larger percentage of the collisions can be effective. Besides the nature of the reactants, surface area, concentration, and temperature, there's one more important factor that can influence a reaction's rate. In a hydrogen peroxide solution, the hydrogen peroxide slowly decomposes into water and oxygen. Occasionally, a tiny bubble of oxygen forms. Now, we warm the solution. As we expect, this increases the reaction's rate. Now watch what happens when we add a solution that contains iodide ions. The reaction rate changes significantly. The iodide ions act as catalysts. Catalysts are substances that can have profound effects on the rate of reaction. They work by providing what is called an alternate reaction path. For example, iodide ions change the reaction path by which hydrogen peroxide decays into water and oxygen. Instead of the slow steps by which hydrogen peroxide, H2O2, normally breaks down into water and oxygen gas, the catalyst triggers a new set of steps, which happen to go very quickly, one after the other. The products of these reactions are water, oxygen, and exactly the same amount of catalyst as we added at the beginning. The catalyst appears unchanged, but it's made the reaction's product form at a faster rate. To understand how, think of a reaction path as a route over a mountain pass. It takes a certain amount of time and energy, activation energy, to get up to the top of the pass. A catalyst provides an alternate reaction path, a different set of steps involved, a sort of tunnel through the mountain that's not as high a climb, that's easier to travel, and that requires less activation energy. Different catalysts affect reactions in different ways. For example, it's very difficult to make sugar actually burn. Heating it will turn it brown and eventually char it. But oxidation will not continue without an outside supply of heat. But with the proper catalyst, sugar will combine with oxygen so fast that it supports a visible flame. Inside our bodies, we also oxidize sugar for nourishment and for energy. But we need to burn it more slowly. In our bodies, catalysts called enzymes are at work. These substances also let sugar burn, but along slow, complicated reaction paths that release energy at a slow, steady rate. In most living organisms, this slow oxidation takes place in the mitochondria of their cells during the process of cellular respiration. Nerve impulses stimulate the production of a chemical at the ends of a nerve cell. The chemicals, neurohormones, transfer the impulse to a neighboring nerve cell. Then enzymes are released that destroy the hormone in an extremely rapid reaction, making the nerve cell ready to accept another message in a fraction of a second. So far, we've considered reactions as if they only went one way, reactants turning into products. But any reaction is really a two-way process. For example, when potassium bromide and chlorine gas are combined, some of their particles collide, and some of these collisions have enough energy to result in a reaction. In this case, the result is the formation of potassium chloride and brown-colored bromine gas. But at the same time that the potassium bromide and chlorine are reacting, increasing numbers of bromine gas molecules and chloride ions react in the opposite direction. Eventually, the forward and backward rates strike a balance. This is the condition that chemists call equilibrium. When a reaction has reached equilibrium, it may seem as if the reaction has stopped, but it hasn't. Both reactions are still running along, but balancing each other. We can upset that equilibrium in a number of ways. One is by increasing the amount of the original reacting substances. Equilibrium can also be upset by changes in temperature. Here, some molecules of colorless dinitrogen tetroxide, N2O4, are breaking down into brown nitrogen dioxide, NO2, while some NO2 molecules are reforming into N2O4. N2O4 was one of the chemicals used in the reaction that propelled the Lunar Excursion Module off the surface of the Moon into orbit. And nitrogen dioxide, you know, is a constituent of smog. Now these gases are at equilibrium. What will happen in a moment, as we heat these gases, relates to a special characteristic of chemical equilibrium. In every pair of reactions, one reaction is always exothermic. That means that it gives off energy, usually as heat, but sometimes as both heat and light. The other reaction is always endothermic. It has to absorb energy as it proceeds. In the equilibrium we're watching, the formation of N2O4 from NO2 is exothermic, energy releasing, and the opposite reaction is equally endothermic, energy absorbing. When this mixture is heated, the rise in temperature gives a special boost to the endothermic reaction, the breakdown of N2O4 into the brown NO2. Of course, when we cool the mixture, the opposite happens. Now, more colorless N2O4 begins forming, and the gas in our vessel turns pale. In general, adding heat tends to shift the equilibrium in the direction of the endothermic reaction. The nature of the reactants, the surface area, concentration, temperature, catalysts, these factors all affect the rate of reaction. We can see most of these factors at work in a large industrial process. This plant manufactures ammonia by the Haber process. The Haber process depends on a simple chemical equilibrium between nitrogen, hydrogen, and ammonia. Nearly 80% of the air is nitrogen gas, relatively inert at low temperatures. In nature, lightning can provide the energy that allows nitrogen to combine with hydrogen from water molecules and form ammonia. This is a fast, but not very controllable reaction. To be practical, an industrial process must be designed to operate as quickly as possible, but still at a rate that remains controllable. The Haber process was shaped to accommodate the properties of hydrogen, nitrogen, and ammonia. Hydrogen gas and nitrogen gas are piped into the system toward a main reaction chamber. Here, the Haber process increases concentration by greatly compressing the gases. As the gas's concentration increases, the reaction grows more productive. The Haber process also uses increased temperature. This speeds up both the forward and backward reactions. But unfortunately, the reverse reaction is endothermic. Too much heat will break down the ammonia faster than it forms. So chemists compromise by using an intermediate temperature, about 500 degrees Celsius, warm enough to hurry the reaction, but not so hot that it seriously reduces the amount of product formed. Within the reaction chamber, the Haber process also uses catalysts, mostly iron, iron oxide, and potassium aluminate. Since they change the pathway, but not the initial reactants or the final product, catalysts do not change the reaction's equilibrium. But they do speed up the rate at which the reaction reaches equilibrium, saving considerable operating costs. Most of the ammonia produced by this method will be used for fertilizers or in the production of synthetic fertilizers. With its additional uses in refrigeration and in the chemical industry, ammonia is one of our most important compounds. The manufacture of ammonia is just one of thousands of processes that depend on reaction rates and our ability to control the factors that influence them. The nature of the reactants, the surface area of solids, the concentration of the reactants, the temperature of the reactants, and catalysts. These chemical processes are important not only in the industrial world, but also in the world of nature itself, where chemical reactions have been going on since the Earth was formed.